So it sounds like we've got these things more or less sorted out. I mean, we now know they're associated with supernovae, and we can explain the apparently incredible fluxes by having this whole thing beamed, which is a kind of plausible thing to happen given that the star is exploding. But that's clearly only half the story. Remember, early on we said there were actually two classes of gamma ray bursts. These are the long, soft ones. What about the short, hard ones? We haven't talked about them so far.
Yeah, so the reason we haven't talked about them is that the Beppo-Sachs satellite and the Hetty 2 satellite that followed, neither were very sensitive to these short, hard bursts. They just really didn't see any of them. They only found these objects, and they could only find these once a month, roughly. So it really took the launch of a new satellite, a satellite that was called SWIFT. It was launched in November 2004 by NASA, and it was an order of magnitude more sensitive than the previous satellites at looking and identifying the locations of these short, hard bursts. So we didn't have to wait too long. In May of 2005, SWIFT detected its first short, hard burst. And so we all slewed our telescopes, and here's an image, I believe, taken with the Keck telescope. And when the Keck telescope is the largest telescope on planet Earth, and this image showed a big elliptical galaxy at a redshift of 0.23.
So that's pretty nearby compared to most of the long soft bursts. So here's the error circle. We know that radiation is coming from somewhere in here, and so it looks like it could be just something in the outskirts of this galaxy. But what are these little things labelled over here?
So all those little things are other galaxies that are just behind this galaxy, because when we're going very, very faint here. You know, we're going much fainter than you normally go with an image.
So by just behind, you mean you're 10 billion light years behind?
Yeah, these could be 10 billion light years behind. They just happen to be, when you look to very faint levels, you can see there are just galaxies everywhere across the sky, and those just happen to be ones that coincided with this error circle.
Did we see anything optical that flashed, got brighter and then fainter?
There was nothing here at all. So really different.
So we're not seeing any visible light, so it kind of rules out a supernova, unless it's hidden by some massive dust cloud.
Yep.
And either, whatever it is, that didn't emit light but emitted lots of hard gamma rays, was either something to do with the outskirts of the galaxy, or it was to do with these much further away small galaxies.
And of course, the energy budget, if it's really far away, is orders of magnitude larger than if it's really nearby. Now, these galaxies are kind of interesting. Elliptical galaxies don't have any star formation. There's no big stars in them.
Yeah, they all formed all their stars in a big rush at the beginning, and since then they're just getting aging and aging. So they've only got the small stars left, so you wouldn't expect to have any new black holes forming in them.
That's right. So what we needed to do was to simply wait, because SWIFT was able to detect these short, hard bursts on a regular basis. And when we waited until July, then we got to see two. So the first one, the next one, the second one we were able to look at was on July the 9th. And this object turned up at a redshift of 0.16. And I should actually say this object was detected by Hetty 2. This is the only short, hard burst it ever detected. It took 3 or 4 years after it was launched to be found, but it found one just after SWIFT was launched.
And was this time we actually saw something that got brighter?
Yeah, in this case there was a flash of optical light. It faded very quickly.
It's not a supernova, it was something
But there
else.
was no supernova. It was just a flash, which we think is whatever exploded, crashed into some gas in the galaxy, and that gave us the flash of light.
This is a bit different. It's quite nearby, like the last time.
Yep.
But this is an elliptical galaxy, so that's far too rough-shaped for that. This is an irregular galaxy.
Yeah, so that's a star-forming galaxy.
So it could have been a supernova. Star-forming galaxies do have the massive stars, but if it was a supernova, it would have stayed bright for weeks, not just minutes.
Exactly. And then 3 weeks later, another SWIFT short, hard burst was detected. And this one, again, in an elliptical galaxy. And you can see, again, a short flash that faded away quickly. And this one was, again, at that redshift of 0.26. So there's a pattern emerging here.
Yeah, I mean, if it was just one thing that was nearer nearby galaxy. It could just have been a fluke, it could have been a background source. But we've now got three things, all of which are close to galaxies that are only maybe 1 billion light years away. That's been to look like a pattern. These things are actually not coming from distances of 10 billion light years, they're coming from distances of 1 billion light years, which means they're actually much less luminous.
That's right, because even in gamma rays, they're much less luminous than the long, soft ones.
So lower fluxes to begin with, and
Yep.
then they're 10 times closer in. So we're talking things that are hundreds, thousands, tens of thousands, sometimes times fainter than the short, the long soft bursts.
Yes, exactly. So these really do appear to be a different beast altogether.
So these short hard bursts are very different things. We don't see a supernova associated with them, and in fact they're often in elliptical galaxies, not always, but elliptical galaxies shouldn't have any massive stars left that could actually form massive black holes. So supernova model seems to be wrong. They're much less luminous. They don't have very much optical flash, much briefer and much fainter. So they're obviously quite different beasts. What could they be, Brian?
Well, their properties seem to indicate that they are something to do with an old stellar population, one that's been around for a long time because of those elliptical galaxies.
So that means some old lower mass star. So we're not talking about massive stars, we're talking about some star with a lower mass that therefore can last longer. But how could these lower mass stars explode?
Well, it might well be that they aren't lower mass stars now, but they're the remnants of massive stars from the past. So I think the best idea is this one. Imagine you have two neutron stars in a binary, and they can merge, and when they merge you have all that gravitational energy of two things that are more massive than the sun, separated by 10 kilometers, coming together. So you have a huge amount of energy to give you a flash of gamma rays.
So in this case it would have been massive stars that formed back when the elliptical galaxy was young.
Yep.
And they went supernova, produced the two neutron stars, which have been orbiting each other. But there's a problem here. You put two neutron stars in orbit around each other, angular momentum is conserved. They'll stay in orbit. Why would they merge? Why wouldn't they just keep on orbiting for the next 100 billion, 1,000 billion years? And they have to get rid of energy somehow, or angular momentum, to actually fall together.
Yeah, you're right. And they actually have the peculiar ability to merge due to what we call gravitational radiation. So Einstein's theory of general relativity says if you take two orbs or two stars and you have them orbit each other very closely in very, very strong gravity, that you end up putting these waves out where space literally goes and so a gravitational wave is where space gets bigger and smaller, and so that of course is energy that's leaving the system, which means that the orbits have to get closer and closer so as to conserve energy. And so that can, over billions of years, bring these two massive objects together.
So at some point we may well learn a lot about these things and confirm what they really are from gravity wave astronomy, but it's not quite there yet. Brian, is there anything we can do right now?
Well, one of the interesting things about merging two neutron stars together is there's neutrons everywhere. And neutron stars aren't just made of neutrons. They also made of things like iron and other elements. So imagine you take a bunch of neutrons and mix it together with other elements. You get this interesting nuclear process. So here I plot essentially how many protons there are in an element versus how many neutrons there are, and the little black line shows you where all of the stable elements are, and then as soon as you get off that black line, things are unstable. So imagine you start off with an atom and you bombard it with neutrons. Then it turns out it will produce a new type of element, which becomes very unstable. It'll eventually decay, but there's still lots of neutrons around. And so you can literally go through on this diagram and make something and then decay and make something and decay, and you can work your way all the way up to form everything all the way up to things like uranium.
This is always a problem. We explained how you can form things as far as iron, but as you know on Earth there are many elements heavier than iron, like gold. So the idea here would be you take something, maybe iron that's already formed, and you'd bump it up neutrons. That would then decay, moving this way, and then make it bumped up again, and then decay, and zigzag its way up here.
That's right. So this is what's known as the R process in nucleosynthesis, as we would say. And it's always been a problem because we've never quite been able to figure out where it might occur.
Yeah, but the textbooks say it happens in normal supernovae, but...
Yeah, and all the simulations that we do of supernovae don't quite get it to happen. It's the only place we can think of until someone had a brilliant idea a few years ago that maybe it occurs in these mergers of neutron stars. And so the simulations, and here is sort of one of the most recent simulations, and what you're seeing here in just sort of 3 quick frames are 2 neutron stars coming together, and where the gold colored stuff is where the gold is formed through this rapid process, the R process. And so this model actually predicts that you can make a lot of these heavy elements when you merge these things together.
Well, that would explain the mystery of where all these heavy elements come from. But is there actually any evidence this really happens?
Well, one of the predictions is that when you merge these things together, this stuff isn't just gold, it's radioactive, you know, anything you can imagine, technetium, who knows, weird isotopes. And there's not a lot of it, but it is highly radioactive. So instead of getting a full-blown supernova, you should get a tiny little supernova.
Yes, you remember that most of the light of a normal supernova is actually not from the initial explosion, it's from all the radioactive elements decaying afterwards. So here you're not getting as many, but they're highly radioactive, so you should get a little mini supernova.
Yeah, and the big problem is most of the radioactivity just leaks out without forming optical light because there's just not much of this stuff, and it just, normally the radioactivity inside of a supernova can light up the supernova from inside. In this case, there's nothing to light up because almost everything is a black hole, just a little bit of this junk hanging around. But the models suggest that you should get a tiny little supernova that has a peculiar property, which is that all of these heavy elements absorb all the ultraviolet and optical light. So you should get a little tiny supernova that emits almost all of its energy in the infrared.
And has any of these things been seen?
Well, we really hadn't had anything close enough to see until 2013. And so in 2013, one of the nearest by of these short hard bursts was detected in this galaxy. And here with the Hubble Space Telescope, you can see this tiny little smudge is apparently that tiny little supernova predicted by this model for producing gold. And it put its light out exactly where it should, and it was about the right size, you know, right brightness.
So not quite proof yet, but it's been to look suggestive that maybe the heavy elements, for example, the one that makes up the gold in the ring, actually has come from one of these gamma ray bursts with these little pathetic little red supernovae.
That's right. So the pot of gold really does lie not at the end of the rainbow, but at the end of the short, hard gamma ray burst.